independent. So the right picture to think about is not this. In case H is hyperbolically embedded, the whole graph gamma sub G looks, this graph, looks like a tree with apples. And these apples are cosets of gamma sub H. Here is the main apple. Okay? So in this situation, it's clear that by gluing copies of S to different copies of gamma sub H, you don't distort the metric into the first glued copy too much. Well, you still have to prove this, of course, but that's the intuition. The proof is a little bit technical. Nevertheless, we get this theorem now.
What's the metric? Since S is not geodesic,
well, you just take the induced metric. So the metric in this copy is just you take the smallest metric, which is bounded. The largest metric, which is bounded from above. So here is bounded by the metric on S. Inside edges is bounded by the natural metric on edges, and inside the carry graph is bounded by the natural metric. That's what we call induced metric. So first you say that the distance between any two elements here is the distance in S. Here it's just the distance inside the mesh. Here it's the distance just inside the graph. But that's not a metric. It doesn't satisfy the triangle inequality. But then you make it to satisfy the triangle inequality by saying that it's a infimum over all decompositions, over all sequences of points, blah, blah, blah. This is kind of standard construction. So if you think about the definition of an induced metric, whatever definition you come up with will be equivalent to what we are doing. That's why I don't want to explain the details. Okay, well, how good is this theorem? How general is this class of hyperbolically embedded subgroups among the subgroups with solvable extension problem? Quite general. For example, we can prove the following corollary for hyperbolic groups. If G is hyperbolic and H inside G is has solvable extension problem, then H is quasi-convex. Conversely, if H is quasi-convex and almost normal, then the extension problem for H inside G is solvable. So, well, if J is hyperbolic and H has a solvable extension problem from the proposition above, we get that H is finitely generated and undistorted, which is equivalent to being quasi-convex. Conversely, if it's quasi-convex and almost malnormal, then by result of prime bounding, you know that G is hyperbolic relative to H, which means that H is hyperbolically embedded into G, and then by our theorem, the extension problem is solved. There is, of course, this gap. So here we just have quasi-convex, here we have quasi-convex and malnormal. Well, here's an example. If you take G to be the free group on A and B, H to be the cyclic subgroup generated by A squared, then the extension problem for H in G is solved. So this example shows that neither of the two conditions is necessary and sufficient. Because here, well, at least being malnormal is not sufficient. And being quasi-convex is not, being malnormal is not necessary. And being quasi-convex is not sufficient because of example number 3, in which case the subgroup is quasi-convex, but the extension doesn't exist. So why is this true? Well, first of all, you have to prove, and this is kind of easy, that the extension problem for H inside the cyclic subgroup generated by A is solvable. So first you extend an action of H to an action of the cyclic subgroup generated by A, and then the cyclic subgroup generated by A is hyperbolically embedded, so the action extends. And well, it would be nice to have a clear algebraic condition which is sufficient, which is a necessary and sufficient condition for a subgroup of a hyperbolic group to have a solvable extension problem, but at this point we don't have it. I mean, you can somehow reformulate things, but we don't have a nicely looking condition.
Your positive examples are Frattini embedded and your negative examples are not Frattini embedded.
Well, you need a little bit more than, no, Frattini embedding is not the condition.
But that's not shown by these examples.
Okay, not with this example, but I can tell you examples which are, well, you can take an involution which switches, which acts non-trivially on H, then H is not Frattini embedded, but still every action extends. Takes the dihedral group, takes the infinite cyclic subgroup. It has a solvable extension problem, but it's not Frattini embedded. So there is a condition which we suspect is sufficient and necessary, but which looks like what you suggested, almost like what you suggested. We don't know yet. Okay, so now, as I said, there are some applications of this to the study of acylindrical hyperbolic groups. And what are the applications? So now this is the subject of another paper with Karaminava and Sahanova Subramania. So we want to study for every group, there may be several acylindrical actions on hyperbolic spaces. So let's try to study all these actions up to some measure of equivalence. Moreover, it turns out that you can compare these actions. You can say what it means that one action is bigger than the other. And you compare them according to the amount of information these actions give you about the group. So here is the definition. Let's say that given two actions of the same group, G on S and G on R, we say that the first action, we call this action A and this action B, that A is smaller than B if, let me say, if the actions are co-bound. So I restrict to co-bounded actions here because things look nicer in this situation, and you can actually work in terms of generating sets. Well, we say that the first action is smaller than the other action if there exists a coarsely H equivariant Lipschitz map F from the bigger action, from the space of the bigger action to the space of the smaller action. Yes, coarse G. So the idea is this. In many cases, you have one action of a group on a space, then you contract some parts or collapse some parts of this space, you get another action. clearly after collapsing, this new action gives you less information about the group than the previous action. And this definition attempts to formalize this situation. Okay? Now, this is not an order relation, but it's a pre-order. So, in the standard way, you induce an equivalence relation. A is equivalent to B if A is smaller than B and B is smaller than A. And the equivalence classes, which I denote in this way, become ordered. So now on the set of equivalence classes, let's call it A of G. That's the set of equivalence classes of co-bounded actions. Well, on this set, you have a partial order induced by the pre-order. So this becomes a partially ordered set. Well, except that you have, if you want to call it a set, you have to restrict the cardinality of spaces you are acting on from the very beginning. Otherwise, it's not a set. Like a set of all spaces is not a set. But let's assume that all metric spaces have cardinality at most continuum, and then everything is the same. So what is an acylindrically hyperbolic structure on a group? An acylindrically hyperbolic structure on a group A is an equivalence class of a co-bounded acylindrical action of G on a hyperbolic space. So you remember one of the definitions of an acylindrically hyperbolic group is that G is acylindrically hyperbolic if G is generated by X, and the Kerry graph corresponding to this space is non-elementary, the action is acylindrical, and this Kerry graph is hyperbolic, right? So every acylindrically hyperbolic group has at least one non-trivial acylindrically hyperbolic structure. In general, you have the following trichotomy. A, B, O. Caroline Abbott's also reminding myself. The theorem says, the first theorem, which is kind of easy, says that for every group G, exactly one of the following holds. First, okay, let's denote by AH of G the set of all acylindrically hyperbolic structures on G. So, as you can see, I don't require here the action to be non-elementary, which means that for every group there is at least one acylindrically hyperbolic structure, the elementary one. So, the action of G on a point, or rather its equivalence class, is always inside this set. So this set always has cardinality at least one. Now for every group, exactly one of the following holds. Either the cardinality of this set is exactly one, in which case all acylindrical actions of this group have bounded orbits, or the cardinality of this set is 2, in which case G is virtually cyclic, or the cardinality of this set is infinite, which is equivalent to G being acylindrically hyperbolic. Okay? Now this is not very difficult. This actually follows from the classification of acylindrical actions of a group on hyperbolic spaces, which I mentioned in my first lecture, and well, plus some easy tricks related to hyperbolically embedded subgroups. But now we can prove a bit more. In this situation, and this is a more difficult result, if G is acylindrically hyperbolic, well, what we can say about the structure of HAH of G as a partially ordered set. So if you have a partially ordered set, the basic questions are, well, first of all, whether it contains minimal and maximal element. Well, the trivial action on the point is always the smallest element, right? Now, it turns out, and this is true for any countable group, if G is a countable group, then this set, A of G, contains a maximal element, not necessarily large, maximal element. If and only if G is finitely generated. And in fact, in this case, the action of G on its locally finite K graph is a representative of the largest element in this partially ordered set. So here, the situation is more complicated. Acylindrically hyperbolic groups may have and may not have maximal or largest acylindrically hyperbolic structures. So we have examples of groups which do have largest acylindrically hyperbolic structures, for example, mapping class groups. And there are obvious examples like hyperbolic groups. The geometric action is the largest one. For mapping class groups, it's the action on the curve complex, or rather the equivalence class of it. On the other hand, we do have examples of finitely generated groups which do not have largest acylindrically hyperbolic structures. For example, the Dunwoody non-accessible group is like that. So in general, we don't know for a given group how to decide whether it has a largest acylindrical hyperbolic structure or not. So this is a kind of acylindrical accessibility question, and it's a difficult question. We don't know if there exists a finitely presented acylindrical hyperbolic group which is not acylindrically accessible, which means which does not have maximal acylindrical hyperbolic structure. So after you solve these basic questions about maximal and minimal elements, next thing you want to decide is how long can be chains and anti-chains in your partially ordered set. So just to remind you, a chain is a set of elements which is linearly ordered, right? An anti-chain is a set of elements so that any two elements are pairwise non-comparable, right? So in this situation, we can prove that if G is acylindrically hyperbolic, then A H of G has chains and anti-chains of cardinality 2 to the aleph 0. Well, this is maximal cardinality you can expect because, well, at least in the case of a countable group. If G is countable, it's fairly easy to prove that this set has cardinality in continuum. Okay? So it's very complicated. It has chains and anti-chains of maximal possible cardinality. Now, how do we prove this, and what's the relation between this topic and the induced action? Well, here's the idea of the proof. As I mentioned in my previous lecture, there exists a subgroup of G, which is F2 cross finite, and which is hyperbolically embedded in the G. Now, F2 is a retract in this direct product. So the extension problem for F2 inside this subgroup H is solvable. And the extension problem for H inside G is also solved. Moreover, we can add to this theorem about extended actions that if the original action of H on this metric space was acylindrical and the metric space S was hyperbolic, then the same is true for the induced action of G on this new metric space. A new metric space is hyperbolic, the action is acylindrical. So this means that every acylindrically hyperbolic structure on F can be lifted to an acylindrically hyperbolic structure on G. So what it gives us is that AH of F2 is a retract of AH of G. So the embedding of this thing inside this thing is given by the induced action, and the restriction factor gives you a retraction from here to here. Now, if you want to prove something, so it's a retract of this partially ordered set. So if you want to prove that this partially ordered set, so I mean all maps are order preserved. If you want to prove that this is sufficiently complicated, it's enough to prove that this is sufficiently complicated, but this is much easier to analyze, and we use an idea which goes back to the paper to Ilya Popovich, who proved, well, in modern terms, what he proved is that this set contains two elements. Yeah, that's right. So, he found, well, sorry, three elements. So there is trivial element, there is geometric action, he found another one. So then this idea can be a little bit improved, and you can use the same kind of technique to show that this guy is sufficiently complicated, which means that it contains chains and anti-chains of cardinality to value 0. And then we just use the construction of the construction. So I think Carolyn is going to present another application of this construction of the construction. So that's all I wanted to say.
Does H have arbitrarily long finite chains which can't be extended?
That's uncountable chains.
Yeah, but are there finite ones that can't be extended?
Well, every chain can be extended. Well, if you exclude the trivial action, then for any non-trivial acylindrical hyperbolic structure, you can find a smaller one. You can always collapse it into, for every non-elementary acylindrical hyperbolic structure. So in some sense, every chain can be extended down. Well, whether there are maximal elements, it's a difficult question. We don't even know if existence of maximal elements is equivalent to the existence of a largest element. So, I mean, there are lots of questions which are still open.
Yesterday when you said F2 by finite hyperbolically embedded in G or something like that, I just thought this morning, I didn't notice that it really was a direct product, and that was important in what you just said. That seems much less obvious than as an F2 by finite.
Well, yeah, that's a direct product. You have to work a little bit to get direct product.
Could you say anything about what the work involves?
What?
Could you say anything about what the work involves?
It involves some sort of small cancellation arguments. So you start with some lexicodromic elements, but their elementary subgroups may not split as direct product, and then you hook some sort of small cancellation verb in this lexicodromic element, and then you prove that this new element will have an elementary subgroup which actually splits as direct product of its torsion part times the cyclic part. And then you can create two such elements. So it's not very difficult. You have to work.